1 light year sounds strangely manageable. After all, it contains the word one, but 1 light year is not a measure of time. It is a distance of approximately 9.46 trillion kilometers, the distance light crosses during 1 year. And for human technology, that single light year might as well be an ocean with no opposite shore. At Voyager 1 speed, the journey would take roughly 18,000 years. Even at the fastest speed ever reached by a spacecraft, it would still take more than 1,500 years. A futuristic laser-powered probe might reduce the journey to only 5 years, but that spacecraft would weigh just a few grams and carry no humans. So why is crossing even 1 light year still so far beyond us? Before we find out, subscribe to The Cosmic Perspective and click the like button for more journeys that reveal the true scale of our universe. Because the most shocking part is not how long 1 light year takes to cross. It is how little of the universe we would have explored when we finally reach the other side. Light moves through space at approximately 300,000 kilometers every second. In a single second, it could travel around Earth more than 7 times. It reaches us from the moon in a little over 1 second and from the sun in roughly 8 minutes. But allow that light to continue traveling for an entire year, and it covers approximately 9.46 trillion kilometers. That distance is 1 light year. It is important to understand that a light year is not somewhere we could simply point a rocket and reach using enough fuel. The fastest possible traveler is light itself, and even light needs an entire year to cross it. Any physical spacecraft must travel more slowly. And the difference between traveling at the speed of light and traveling at the speeds humans can currently achieve is almost unimaginably large. Our nearest neighboring star, Proxima Centauri, is approximately 4.25 light years away. So crossing 1 light year would not take us to another star. It would not even complete 1/4 of the journey to the closest one. The clearest demonstration of this distance is Voyager 1. Launched in September 1977, Voyager 1 used gravity assists from Jupiter and Saturn to gain speed before beginning its journey out of the planetary system. It is now the most distant human-made object in existence and is escaping the solar system at approximately 3.5 astronomical units per year, roughly 17 kilometers every second. That sounds fast. At that speed, it could cross the Atlantic Ocean in only a few minutes. Yet NASA calculates that Voyager 1 will not become 1 light day distant from Earth until November 18, 2026. 1 light day is the distance light travels in 24 hours, approximately 25.9 billion kilometers. That means nearly half a century after leaving Earth, our most distant spacecraft will have traveled only about 1/365th of a light year. If Voyager could continue at approximately the same speed, covering a complete light year would take around 18,000 years. The Great Pyramid of Giza was built only about 4,500 years ago. Voyager would need to travel for roughly 4 times that entire span of recorded history just to cover 1 light year. And Proxima Centauri would still be several light years farther ahead. Voyager is not the fastest spacecraft humans have produced. That record belongs to NASA's Parker Solar Probe. During its closest approaches to the Sun, Parker travels at approximately 700,000 kilometers per hour. That is around 194 kilometers every second, more than 11 times Voyager 1's speed. But there is an important catch. Parker reaches that velocity while falling extremely close to the Sun, accelerated by the Sun's enormous gravity. It does not maintain that speed while traveling outward through interstellar space. Nevertheless, imagine that it somehow could. Imagine a spacecraft traveling continuously at Parker's peak speed, aimed directly across a distance of 1 light year. the journey would still take approximately 1,540 years, not 430 years, more than 15 centuries. A spacecraft leaving Earth today would arrive long after every living person was gone, after nations had risen and disappeared, and after its launch, civilization had potentially become unrecognizable. And this calculation still ignores the time and energy required to reach that speed, or to slow down at the destination. There is one proposed technology that makes the figures look much more promising: breakthrough. Starshot is a research program investigating whether extremely small spacecraft could be attached to reflective sails and accelerated using a powerful array of ground-based lasers. The proposed craft would be gram-scale nanoprobes rather than conventional spacecraft. The laser would push against the sail, potentially accelerating each probe to approximately 20% of the speed of light. At that velocity, crossing 1 light year would take about 5 years. Reaching the Alpha Centauri system could take a little over 20 years. That is an extraordinary improvement over Voyager. But it does not mean humans are 20 years away from traveling to another star. Starshot remains a research concept. The proposed spacecraft would be extremely small, would carry no passengers, and would perform a high-speed flyby rather than entering orbit around its destination. It would also need to survive collisions with interstellar gas and dust while moving at nearly 60,000 kilometers per second. Research into relativistic spacecraft has shown that even tiny particles could erode, melt, or damage the probe's forward surface during such a journey. 5 years is therefore a theoretical travel time for a miniature probe under ideal conditions, not a realistic travel time for a human crew. A gram-scale probe and a human spacecraft are completely different engineering problems. A crewed vessel would require living space, power generation, food, water, oxygen, temperature control, waste recycling, medical equipment, and redundant systems capable of working for years, or possibly generations. Every additional kilogram would require more energy to accelerate. The ship would then need even more energy to slow down. Reaching a destination at 20% of light speed without a braking system would mean passing it in moments and continuing into space. Radiation would present another major challenge. Beyond Earth's magnetic protection, astronauts would be exposed to galactic cosmic rays and energetic particles from the sun. Shielding can reduce that exposure, but shielding adds mass, and adding mass makes acceleration more difficult. At relativistic speeds, the apparently empty space ahead would become dangerous as well. Individual atoms, gas particles, and grains of dust would strike the front of the spacecraft with enormous energy. A vehicle traveling slowly could tolerate particles that a near light-speed craft could experience as intense radiation or microscopic explosions. The vessel would need protection, repair systems, and perhaps several sacrificial shielding layers. And every one of those systems would increase its mass again. The journey would not resemble the streaking stars commonly shown in science fiction films. At a steady velocity, passengers would not feel themselves moving. There would be no rushing wind, no engine noise outside the spacecraft, and no physical sensation of speed. For long periods, the stars might appear almost motionless. Only extremely precise observations would reveal their positions gradually changing as the spacecraft crossed interstellar space. The sun would slowly become another bright point among countless others. The region between stars is often described as empty, but it is not truly empty. Interstellar space contains thinly distributed gas, dust, magnetic fields, radiation, and energetic particles. The density is extraordinarily low compared with conditions on Earth. Yet even extremely sparse regions of interstellar space can still contain around 100,000 atoms within a single cubic meter. The danger is not the amount encountered at any one moment. It is the accumulated exposure across trillions of kilometers, especially when the spacecraft is moving at a significant fraction of light speed. Even if the spacecraft survived the journey, communication with Earth would become painfully slow. Radio signals travel at the speed of light. From a distance of 1 light year, every message sent back to Earth would require 1 year to arrive. Earth's response would need another year to return. A simple question and answer would therefore take at least 2 years. There could be no live instructions from mission control, no real-time conversation with family, no immediate help during an emergency. The crew, or the spacecraft's autonomous systems, would need to make every important decision independently, and at greater interstellar distances, the silence would become even longer. From Proxima Centauri, a message would require approximately 4.25 years to reach Earth, and the same amount of time for a response to return. A single exchange would span more than 8 years. After completing this colossal journey, the spacecraft might still be passing through the outermost region associated with our own sun. The planets occupy only a tiny central portion of the solar system. Voyager 1 entered interstellar space after crossing the heliopause at approximately 122 astronomical units from the Sun. But the heliopause is only the boundary of the solar wind's protective bubble. It is not necessarily the outer limit of every object gravitationally associated with the Sun. Far beyond the heliopause may lie the Oort cloud, a theoretical shell of icy bodies believed to be the source of some long-period comets. NASA estimates that its inner region could begin a few thousand astronomical units away, while its outer boundary may extend as far as 100,000 astronomical units. That would place parts of the cloud more than 1 light year from the Sun. NASA also notes that the Sun's broad gravitational influence may extend approximately 2 light years. This does not mean a fast spacecraft would remain trapped by the Sun. An outbound craft moving quickly enough would already be on an escape trajectory. It means only that there is no clean wall where the solar system suddenly ends. After traveling for 18,000 years at Voyager's speed, we might still be moving through the distant outskirts of our own celestial neighborhood. The answer depends entirely on the technology. At Voyager 1's approximate speed, 1 light year would take around 18,000 years. At Parker Solar Probe's peak speed, if that speed could somehow be maintained, the journey would take about 1,540 years. A theoretical breakthrough Starshot probe, traveling at 20% of light speed, could cross it in approximately 5 years. Light itself requires exactly 1 year. But no existing spacecraft capable of carrying humans can approach any of those faster figures. And even after crossing the entire distance, we would remain less than 1/4 of the way to the nearest star. Our Milky Way is approximately 100,000 light years across. 1 light year represents only 1,000th of 1% of that diameter. To the galaxy, it is almost nothing. To humanity, it remains one of the greatest barriers we have ever imagined crossing. The universe is not merely vast because its destinations are far away. It is vast because even our first meaningful step towards them could outlast entire civilizations.